Thanks for the introduction, and thanks to the organizers for inviting me and giving me the opportunity to give this talk. So the topic is Feynman integrals, and in particular IBPs and differential equations. And of course, this is a topic with a long history. But the first thing that I'm going to try to do is change history, okay? In the sense that there is a history which is known to most people, and then there is an ancient history which is by now sort of known to quite a few people, but definitely not as many. So there is a historical part to this talk, and then I will sort of use this old technology, which is being actively explored and rediscovered in a slightly different context. So I will briefly discuss the properties of Feynman integrals as projective forms in Feynman parameter space. And then I will discuss, still roughly using these old papers, how this technology naturally gives rise to identities between generalized Feynman integrals, which in fact are what we now call, what we have called for many years, integration by parts identities, or dimensional shift relations. And I will give some examples, and then you know, so far we are far from having an actual algorithm, but there is clearly an algorithmic direction in this kind of work. And I should say that there are other groups that are quite ahead in this. There is Yang Shang here, who is one of the authors of NEAT IBP, and I'm sure there is a lot of overlap between what I'm going to say and what they are doing, although they are apparently using something different, but it's clearly related. And I should, of course, say that this has been done in collaboration with my former master student, Daniele Artico. In collaboration, you know, is always a euphemism. When there is an old guy like me, it actually means that he did all the work. And I emphasize this because he will be soon looking for postdoctoral positions. He's finishing his PhD in Berlin. Had a paper out this morning. But okay, so ancient history. So this man, who is probably unknown to most of you, is Tullio Regge. And this is a picture from probably the late 60s or early 70s. And the definition that I'm using of ancient history is that I'm discussing stuff that happened while I was in elementary school. Okay, so that's clearly ancient history. So if you think about you know, the story of Feynman integrals, I mean, of course, I'm going to misquote and not cite the proper people, but the story that, roughly speaking, we have in mind is that in 1981, I think, Chitirkin and Kachov came up with the idea of integration by parts identities in dimensional regularization and in momentum space. And this enabled them to do a bunch of integrals that were impossible at the time. So, for example, they computed the for-loop beta function after that. And then it took roughly a decade. Tarasov came up with the idea that you could actually compute Feynman integrals using differential equations. Then you would, you would show that they obey some differential equation. This was still in momentum space. And then you would impose some initial conditions, which are typically easier, and then you would solve them, and you would never have to compute an integral, which, of course, simplifies things quite a bit. And then this was picked up by Remidi, and then by German and Remidi, and sort of an industry was born in 2000, so it's another 10 years. Stefano Laporta came up with his algorithm, and then many versions of this algorithm are currently in use, you know, Kira, and fire, air, you know, water, earth, I don't know, all of these techniques are available. However, a few years ago in Torino, we had a Regge celebration, because Regge was, of course, from Torino, and I was given the task to give a talk about Regge's contributions to phenomenology. Of course, much of Regge's work is about gravity, but of course, Regge is still the same Regge of Regge poles, and so I dug up in history, trying to trace, you know, a history of, you know, the idea of Regge in actually the very late 50s that gave rise to the entire industry of Regge poles and Regge cuts and the high energy limit. And many people in this audience are quite knowledgeable about this, and it's a story that it's ongoing. And then when I was looking through the literature, I found a paper, and not actually by Regge, I'll show you in a second, and the title was Differential Equations for Feynman Integrals. And this was a paper from 1972. That's 10 years before even the IBPs identity. So I said, what? And then you start looking, and okay, so it goes even further back. So this is 1967. These are some lectures by Tullio Regge in a meeting that was called Battelle Rencontre. And this would make you think that Battelle is someplace in the French Alps, maybe near Les Houches, but actually Battelle is an institute near Seattle. So there's nothing whatsoever to do. It's not French at all. So you see, he's talking about algebraic topology methods in the theory of Feynman relativistic amplitudes. And you should substitute the word Feynman graph for Feynman relativistic amplitude. Okay? It's just what they called it back then. So he's really talking about Feynman graph, and then you realize that this is an incredibly modern title. I mean, this is something that you could publish, it could have been published yesterday. This is the stuff that a lot of people are now working on. Sebastian Misera and Eric Panzer and Stefan Heinzel and many more. So these are lectures. They are difficult. The language is very mathematical, so possibly many of you will find it easier than me to read this stuff. And the language is old, right? So this is long before many of the techniques that we use were developed. For example, dimensional regularization doesn't exist. Infrared divergences are regulated by masses, so many tools, even of mathematics, of projective geometry and similar, they were not as far developed. However, if you have patience and you go through these lectures, they are quite interesting. And then you discover some statements which are really remarkably modern. So, for example, at some point, just doing some general remarks, Regge says these Feynman integrals. At the end of the day, there will be some generalized hypergeometric functions, right? And this is, again, a remarkably modern thing to say, right? This was rediscovered rather recently. And then he say, well, okay, so in fact, I cut because I just wanted to mention, but he has some sort of homological arguments because what these people are looking at is the set of singularities, the solutions of the Landau equations. And they want to understand how what happens to the function that the integral computes when you go around these singularities. So there is a homology, there is a homotopy. And based on homology says, well, at the end of the day, all of these literally means any mass is external, internal, that they are more scared of zero mass than they are of generic masses. At the end of the day, they will be hypergeometric functions. And because of that, they will satisfy some differential equations, lo and behold. And then he will show how to derive these equations in principle, and I underline in principle because this is a very mathematical discussion. But then he says, well, actually, at the end of the day, these equations will be Picard-Fuchs, okay? And then you look at present day, and I've added a few references, and then you realize that starting about 5 years ago, possibly also before, quite a few people have been trying to make these statements very concrete. Now, we don't talk of generic hypergeometric functions, but we talk of A hypergeometric functions, we talk of GKZ hypergeometric functions. So this is like the incarnation of this is like a prophecy, right? He didn't really have a solid argument or a precise definition, but he sort of knew where he was going. I have put ... here, because of course this is an immense literature, right? And now for 20 years we have been, 25 years we have been looking at sets of differential equations, which were typically derived in momentum space, in modern times, also in parameter space. So you can't even begin to put references here. There are an enormous number. And also Picard-Fuchs actually was prophetic, and it has come back. So this is a paper about 11 years ago by Stefan Heinzel and collaborators. And then last year, well, 2 years ago, Peter Van Hove wrote something about Picard-Fuchs equation for two-point functions for multi-banana integrals, so to speak, and the discussion continues. So a lot of things were known back then, and it was literally quite a surprise, okay? So it was not just these lectures, so these people published papers, I'm gonna show you a few. So in 1969, so this was 1967, in 1969, a group of people, a collaborator of Regge who was also in Torino, Ponzano, and then Speer, who was back then. I mean, they were all at the institute, but Ponzano also had his career in Torino later on. They looked at these very interesting graphs, which of course are also very modern, and a lot of work in recent years has been done about these graphs. Now, the viewpoint was a bit different, okay? And in fact, there is this slightly mysterious mention of a monodromy ring, which is something I would really call it a monodromy group. But so literally, these people were looking at these graphs for arbitrary masses, and now we know concretely, like for example, just if you look at the sunrise with 3 masses, different masses, is very much more complicated than the sunrise with just, with equal masses. So they were looking at these graphs and they were trying to construct the monodromies around the singularities defined by the Landau equations. And these, for some reason that I don't fully understand, they talk about a ring and then a group ring, but anyhow, these are the monodromies. And they succeed. They succeed in this. So they have an explicit matrix representation, which again suggests that it's indeed a group that they are working on. And the dimensionality of these matrices is 2 to the n minus 1 for and the n leg. And then they are sort of, I don't know if you define it aristocratic or something. They don't actually do any calculations. They are happy with having found a group. Right, that's because what they were interested in was the formal structure of Feynman integrals, and they didn't have to. It was completely unthinkable to do any kind of phenomenology with this stuff like we have been doing for a couple of decades now. So this was 69, and then they did the endpoint one-loop graph. And here also they have a result, again, a very formal result about how you can build a certain group. Here the number of equations is a bit delicate because it depends, this is n legs in dimension d, and how many equations you have depends a bit on n and d, but curiously enough, coincidentally, the largest, I mean, the most general case is again 2 to the n minus 1, but now n are the number of propagators along the loop. And this was 1970. And then they just combined the two things. Ponzano left and Regge, Speer, and Westwater. You see, this is the one loop graph, and it is dressed by the bananas, right? So this is a more general class of multi-loop graphs for which they also have results. Now, these results are very, very formal, so they are not immediately useful for practical calculations, although they are very, very general. So in terms of what we do, we typically start with a massless integral, massless legs. We have dimensional regularization. They didn't. And then, slowly we put 1 mass, we put 2 masses, it becomes more complicated and all that. So they were sort of going backwards in that sense. However, that same year, 2 collaborators of Regge who were in Torino, Giuseppe Barucchi and Ponzano, they actually took this result and they made it practical. And so this is the paper I happened upon. It's called Differential Equations for One-Loop Generalized Feynman Integrals. And actually what they are happy about is that they have an explicit construction of a system of differential equations that closes in the most general case for n legs for generic masses. And the dimension of that system is 2 to the n minus 1, and they can match it to the monodromies that Regge and Ponzano had found before. So they were quite happy about that, although again, and this is not necessarily as yet a computational tool, not in modern language, but this is very, very close. And in fact, this magic number, so this is like the maximal size that you need for a generic one-loop graph, came up again. So there are very recent papers by Bitun and others, and by Sebastian Misera, in which this is a collaboration that includes Eric Panzer, and you all know Sebastian, I guess. This number arises in a more general context when they are computing, like the Landau discriminant, as they call it, and stuff like that. So what I'm saying is there is a story that started, a long time ago. And so what we started with when Daniele was then my master's student, we started looking at it. So how does it compare? Again, this was not suited for dimensional regularization, the way it was written. However, they were, of course, worried in principle not about infrared divergences. No, everything has a mass, right? In the old days. It's as a side remark, since we have an hour, so I have an hour to fill, let me note this. So these papers, they always start apologetic, right? I mean, they apologize. They start by saying, the S matrix is this great thing, and we would like to bootstrap it, and we would like to know the non-perturbative properties of scattering amplitudes, but it's too difficult. So we apologize, and we will just do this thing which really arises from perturbation theory. Don't tell anyone. Perturbation theory really is not the answer. But, we can play around with perturbation theory, and we get some results. So that's what they did. They were, of course, worried about ultraviolet divergences. So they did introduce a regulator. And the regulator was what we would call nowadays analytic regularization. So they put a non-integer part to the powers of the propagators. These were called the Speer parameters. And actually, I learned yesterday that maybe I shouldn't say Speer. I thought he was German, but actually this guy is called Eugene Speer. And he was at MIT, and he's yesterday amazing. I mean, he wrote papers in the early 60s, and I discovered that he's still writing papers. Okay, so Speer is actually alive. He wrote a paper last month in July. So they call them Speer parameters. And the luck is that actually it's almost the same thing, right? So you can really turn, I mean, the fact that you have these non-integer powers is very, very close to dimensional regularization. And so these techniques actually work. You can do dimensional regularization, and this does not present any major difficulty, which was one of the results in Daniele's master's thesis. Okay, so now I think I'm going to be boring for most of you, but I will compensate for being boring and saying things that you all know by saying them in a really ancient and clunky language. Okay, so the mathematical people among you, they will say, why is it so complicated? This is just projective geometry, and then those who are not working on these things probably find it boring. But after showing Reggio, well, clearly I'm showing Feynman. Maybe I should also show Schwinger, but okay. So let's quickly look at parameter space so that everybody is on board on the same starting line. And of course, I'm using the great review by Stefan, published a couple of years ago, a momentous 650 pages of Feynman integrals. Okay, so this is a Feynman integral. It's a scalar integral. I have made it dimensionless. It's in loop momentum space, and there are denominators which are propagators. This is where the Speer parameters will go. And down here, it's a quadratic form in the loop momenta and in the external momenta, and these are incidence matrices. And the fact that the denominator is a quadratic form is what allows you to do the Feynman trick or the Schwinger trick, which is a completely general idea that Feynman, I think, came up with first. And this is actually, I don't think Feynman realized how fantastic this is, right? Because this really uncovers some deep properties of these integrals, which are not at all apparent in the form in which we get them in perturbation theory. So when you apply the Feynman's trick, then you now get an integral, which is on a set of n Feynman parameters. It turns out there is a delta function, so this is actually n minus 1. This is not a single integral, it's a family of integrals, which are defined depending on these numbers. And I should not forget to say that this nu here is just a sum of all the nu i's for I equals 1 to n, so that this thing is actually dimensionless as defined. And then you get a ratio of polynomials. And these polynomials, they can be written directly in terms of the original denominator. So because it's a quadratic form, then the quadratic form in the loop momenta, then there is a matrix which describes the quadratic piece. There is a linear term in the external momenta. There is a constant. And you can write these polynomials in that way. For example, U is just a determinant of the matrix that you get in the quadratic form and is completely independent of external data. It just depends on the form of the graph. Whereas the second semantic polynomial contains the external kinematic information, the masses and the Mandelstam invariants. However, there are two important things, one which is fun and one which is enormously important. Now, the fun thing is that which you might have expected, that you can describe these polynomials in terms of the properties of the graph, just straight out of graph theory, right? So you don't need to know anything about quantum field theory. This integral is given to you. It is uniquely associated to a graph. By the way, I should note something that might be of some relevance later. So, of course, this usage here depends on a specific decision that you have to make about where you put the loop momentum. Imagine you have, some complicated graphs and you have to decide what you call K1, K2, K3, and you can make different choices. And so there is a whole set of possibilities. And so we don't really want a whole set of possibilities, right? It's easier when you have to write an algorithm if it's just one way, right? And when there are many ways, then it's likely that some ways are better than other ways, and so you have to make choices. And this is a degeneracy which exists in momentum space, but it is completely lifted here. So just in terms of the graph, without knowing anything about field theory, then you define a spanning tree for the graph, which is a graph with no subgraph, no loops, which contains all the vertices. And you can easily convince yourself that in order to find such a graph, you have to cut L legs for an L loop graph. And then you define the first semantic polynomial as this sum over the cotrees of the product of the Feynman parameters that belong to the tree. I think you're very familiar, so any example will clarify what this means. And then if you want a second semantic polynomial, you see there is a piece which is proportional to the first one, and it carries the mass dependence. So in a massless graph, this will not be there at all. And then here, the first piece involves a slightly more complicated object. These are called the spanning two forests. And those you get, but you collect the spanning trees, then you cut one more. And when you cut one more, the graph, of course, splits open into two subgraphs. So then you have really, at that point, you have cut the graph in two. And when you have cut the graph in two, there is a momentum which is flowing out of the first subgraph into the second one, or vice versa. And the two things are, of course, equal by momentum conservation. And so the Mandelstam invariant associated with the cut is sitting here. And then you have the product of the Feynman parameters, which are sitting in the complement of the spanning two forest. And it's easy to make example. So this is fun. You give me a graph, I can give you the Feynman integral, or rather the family of Feynman integrals associated with that graph. But what is instead not fun, I mean, it's also fun, but it's very important, is that the integrand here, when you look at the values of the numbers, then you put them together for generic D, generic news, the value, this integrand is homogeneous of degree 0. So it's a scale invariant. And in fact, it is something slightly more subtle, because if I just say scale invariant, I'm really omitting the delta function. But what it actually means is that the integrand is properly defined in the projective space. And now you start to think about a real projective space. So there would be PR and n-1. But then you can, of course, make it complex. So it's a complex projective space with n-1 variables. And this opens the way, as that was the way that Regge was adopting, to usage of projective geometry. And so, which is a set of very powerful mathematical tools. The Zs? The Zs are the Feynman parameters. So these are you have n, so they are the coordinates in the immersion in Cn. And then there is one constraint, which is here is given by the delta function. But you don't have to use that constraint. So in a second, I will, if I write it as the integral of a projective form, then of course I'm free to choose a representation, a coordinate patch, you must say. So I can use the simplex, or I can just set 1 to 0, so set 1 to 1 or to 0. So you can, so that will be what is called in the literature of Feynman diagrams is called the Cheng-Wu theorem, which is actually not a theorem at all. It's just a statement that the integrand is a projective form. So everybody, I guess, knows this. And now let me, presumably from a mathematical point of view, look at projective forms in a rather clunky way. So I'm sure many of you could do better on this slide. Apologies for that. So the thing is, this thing here is generically, with this definition, it is a projective form. So what is a projective form? Well, you know, if I take the index set 1n, so n for me will be the number of propagators, but can be anything, of course, and I take a subset of rank a, with a any number between 1 and n, then I can build a volume form in this subset. So these indices are ordered with some order that you like. So this is an A form. And whenever you are given that, then you can sort of integrate it, so construct an A-1 form with one less differential. And so what you want to do, you want to drop a differential, and then because at the end you want scale invariance, you want to put back 1 power of these coordinates, and then you need signs because these are forms. So you have to pick your signs in such a way that things work well. And so I define this eta A, which is an A-1 form, as the sum of some zi, and then I have taken that and I have dropped the ith coordinate, I being one of those that I had to begin with, I multiply times that particular z. And I have to define the signs. Okay, I won't bore you with that. There is a consistent way of defining the signs. And then you find that when you differentiate this, then you get precisely the original one just with a number in front, which is the size of the set. And you can easily see what happens, because if you do just 1, 2, 3, then this is what you get, especially if I can get the laser to work, but okay, no. So if I differentiate this, I get, of course, dz1, dz2, dz3, which is the volume form, and the arrangement of the signs is such that I get it 3 times with a plus, and that's what I'm expecting. Then in this space, you define affine forms. When you take these and you multiply them times rational, I have rational in quote, but in the original definition, it's rational functions, which must be homogeneous of degree minus q if you have, little a equals to q, so that this is scale invariant. Right? This is called affine. And then the projective forms are a subset of those. They are those for which it is possible to rewrite them. So this is the same object. I want to be able to rewrite them identically in terms of these forms, which means that basically I have changed the rational function. I have extracted some z to make the etas, and then I have compensated. Of course, there is one less differential, and that doesn't always happen, right? So it's a subset. This is another rational function, homogeneous of degree minus q minus 1. And this is an example with lambda now is supposed to be an integer, and the experts or even the not so experts will recognize that this is actually the integrand for the massless box in some dimension. Right. So good. I was forgetting to say it. So I put rational in quotes, because then at the moment we use the sphere regularization or dimensional regularization, this lambda will acquire a non-integer part. So there will be integer. If lambda was integer, this would be literally rational functions. And what I'm going to do in practice is I'm going to introduce a regularization in which there will be some non-integer part. And the epsilon compensates. Once you do that, yes. I mean, once I decide to put a regulator, lambda will be complex. Well, this I think is it becomes slightly clearer. So the projective ones are interesting because they are a closed set under differentiation, under exterior differentiation, and this is really what allows you to generate identities, because now you have a huge you have a lattice of integrals, and you can walk around using exterior differentiation. Absolutely. The integrand of a Feynman integral, any Feynman integral, is a projective form. It's a projective form, which is that is why this whole thing has any relevance at all. In fact, the set of integrals that described by projective form is bigger than Feynman integrals, and then we can make a few specifications, and we get even in the old papers they were discussing generalized Feynman integrals. They meant any projective form that in particular can be a Feynman integral. Okay, so sorry. Okay, R here, R is an external parameter. It's going. So what you then once you start talking about the external parameters, so R here is going to be S over T. This is going to be the box, and then of course what you would do in real life is go to some Euclidean region where everything is positive, and get a result, and then do analytic continuation. That is of course the safe. I don't know any of you. Yeah, yeah. Sure, and then all sorts of complications may arise, but so this one is an A form, and here the B is Q plus 1. So it's the same thing. It's just an exact rewrite. Yeah. Okay, so for a Feynman integral, you get something like this. So D here, apologies for changing notation, is really the second semantic polynomial. P is some number involving the news and the dimension and the number of loops, and Q contains all these parameters and of course here you get the n-1 volume form, and here what Atul was mentioning, what happens. So this eta, which is of this form, then when you actually choose a patch in projective space, or choose a chart if you want, then you can land on the simplex parameterization, which is what I see, or the Cheng-Bu theorem, which I'm actually mentioning here, will allow you to choose different possibilities for that delta function. So here is so this is a specific case, but the important theorem is that the boundary of a projective form is itself projective. It's not difficult to show this with the definitions that I gave. It's a bit delicate with signs, as always with these things. So I can define an operator P, and you see that this operator takes an A form, which is affine, and makes it into a projective form. So P is non-trivial, so this is not the same as what I've done here, right? So here I've simply said I have a form, I rewrite it, and here I say I have a form and I have an operator which maps me to a different form with the same rational coefficient, but the projective form instead of the affine one. And then when you look at the explicit action of this operator, you find that it squares to 0. And it anti-commutes with exterior differentiation. So if you act with P and then D, so of course P will get you from an A form to an A-1 form, and then D will get you back to an A form. So it's this D dot P and DP and PD act on inside of the space of A form, they anti-commute, and this is enough, essentially enough to actually show that when you do exterior differentiation of something like this, you will get another object which is in the same set. And when you actually do it, this is what generates IBP identities, because now I have a very, very large lattice of integrals with some integer parameters plus some epsilon stuff. And then when I do exterior differentiation, I get some other integral, right? And different news, different Ds maybe, and And I will actually show you the way that this is implemented. And then another, this is sort of, has been known for a long time, but it comes out nicely from this projective framework, is the fact that I can change the domain of integration in Cn. So what I have is I have an integral over the positive subspace, Z1 to Zn. They are integrated everywhere where they are positive, but I have a delta function constraint. That delta function constraint drops the number of variables from n to n minus 1, so it's really an n minus 1 dimensional integral. But because it's really a projective form, then if I integrate on two different domains that have the same domains in Cn, which have the same image in projective space, then the integral is the same. The integrand is not the same, but the integral is the same. And the reason is very simple. If when you integrate this, so imagine this is Z1, Z2, Z3, and this would be the normal domain of integration in which the three Z's sum to 1. And then what I'm saying is I can deform this. I can, for example, drop this point to the plane, or I can pull it up. It doesn't matter. So I can integrate here, or I can integrate here, and the result is the same. And the reason is that alpha, of course, is a closed form. So the integral of a closed form on a closed surface will be 0. And the closed surface is made by this and that, and then there is the boundary. But on the boundary, eta vanishes because we have constructed it so, right? So if you look at the typical eta, you see that if I decide to set z1 equal to constant, then this vanishes because it has dz1, this vanishes because it has dz1, and this vanishes because it has z1, right? So I have the integral of a closed form and the null boundary term, and then it means that I can integrate here or there, or I can, just set the value of one of the parameters, and this is commonly described as the Chang-Bu theorem. It means that inside the delta function, instead of having the sum of all the z's, for example, you can just set one z to 0 and have the sum over n minus 1, n minus 2, n minus 4, have just one z. You can do any number of things, which in fact are done in the programs that do actual calculations. So nice. And now about IBP identities. So I didn't resist. I'm sorry, this is really an Italian joke, right? So I Googled IBP, and I found that this is a medical product that is sold in Italy. It's called, for some reason, IBP Plus, and it is actually an integratore alimentare, which in Italian, it means food supplement. But integratore is also an integrator. That is something that does integrals. So I don't know if we will ever have software, but if we actually write a program, instead of calling it neat IBP, maybe we will call it IBP Plus. And then we will ask them for money, because it will be, of course, free advertising. Anyhow. Yeah, we will. That's a good integratore elementare. That's pretty close, actually. Yeah, I just did it. Look, that's what, of course, they did, because they wanted to do analytic continuation in the most general circumstance. So they like to have anything complex. They like to have everything complex. Exactly. In practice, I will never really use the information that the Feynman parameters can be complex. What you really do at the end of the day is just complexify the external parameters, so the Mandelstam invariants and the masses. So, there is really, I should say, we could use, as far as I can tell, real projective space. It would be the same, as far as I can tell. Okay, so suppose then that you pick a set of coordinates in this projective space. And so, for example, we choose the standard simplex as an integration domain. So we decide that the constraint we decide to apply is that the sum of all the z's is 1. And then I can express one differential in terms of the others. And then you can simply just write it down. And you realize that this integral is actually exactly this integral. Okay? And it's not the only way to do it. You could do something different. You could not choose the simplex. You could choose some subsimplex. It will still work. But this is just this step, which is actually easy to do. Once you write it down, is what tells you that any Feynman integral is actually a projective form. Of course, Q and P and D, they have to be defined as rational functions with a possible linear addition of some complex parameter epsilon or lambda, but so that the thing is homogeneous of degree 0. Then it works. And then, because I can differentiate the projective form and get another one, then it means that I can start with a Feynman integral and express it in terms of a bunch of other Feynman integrals. And if I'm lucky, they will be simpler. So I will come down from some really seriously complicated Feynman integrals and drop down to a bunch of integrals that I can actually do, right? Or that I know already for some reason. And so one way to do it, I realize it looks slightly backwards. So let me define an n-2 form. So I went down 1, and I define it with the same Szymanczyk polynomial in quote, but to the power p minus 1. Then I put some numbers and signs, which are just to simplify the next step. And here, I just put some arbitrary polynomials, which I will have to choose. These polynomials are just chosen such that the homogeneity property is preserved, okay? So that this thing is still homogeneous. And then, so I am now looking at an n-2 form, and I differentiate it. I get an n-1 form. And of course, it's made of 2 pieces. One piece, I get derivatives of the numerator. And of course, I have chosen the signs in such a way that this will become the projective form which appears up there. And then the second piece, I differentiate the denominator, and then this number has gone up, right? P minus 1 has become P, and I still get to the full volume form up there. And this is an identity which ties together some Feynman integral. So the way in which we are going to use it is that we are going to decide that we don't like some integral. Okay, some integral is really complicated. I don't want it. And then I will try to express the numerator of my integral in terms of this. So using derivatives of the second Szymanczyk polynomial and choosing these in some allegedly smart way. So here's my complicated integral. I'll bring it here. And then this will be expressed as a sum of objects that are actually simpler for 2 reasons. One is because you get a always smaller power of the Szymanczyk polynomial here. And the other one is the boundary term, right? And the boundary term is simpler because you drop some, you drop a leg essentially. The boundary term becomes a simpler integral. And actually Barucchi and Ponzano, they didn't really look at the boundary terms. They just said, okay, we look at the cases in which the boundary term is 0. So they didn't actually write the full result, but it doesn't matter. The boundary terms are actually very, very interesting. In the normal momentum space IBPs, you also, when you're lucky, you get down to integrals that have lost some propagators and have simpler topologies. And the way that happens in this context is because you have boundary terms which are not always 0, and often, in fact, they are quite interesting. So this is in some sense like the master equation, although I will later write it just changing places, right? Yeah. Yeah. Not any polynomial is a Szymanczyk polynomial, right? So what must happen here is that D is a graph polynomial, and Q is the other polynomial of that graph. So D and Q are tied. So D contains, for example, a piece proportional to Q. Yeah. Yeah, in principle, I can generate, or I can use in intermediate stages, something which is not, that it does not actually correspond to a graph. It's possible. And of course, in some sense, you don't want any procedure like this to be an art form. You want to have an algorithm. But here, it's clear that at this stage, it's an art form choosing H high, right? And I will try to make that better in a while. Of course, Reggie and company, they did make some choices, and now we're going to use those. So at one loop, it's really simple in the sense that, and well, really simple, maybe it's a big word, but this is what Barucchi and Ponzano did, and they made a choice for HI. So first of all, the generic one loop integral with n legs, you can write in full generality. You see, this is the family of integrals that is determined by the powers of the propagators. There are some gamma functions. And the denominator at one loop, you can make it really simple. You define an n plus first variable, which is just the sum of all the variables, and an n plus first power, which is simply related to the powers that you already have. You define what is called a Cayley matrix, this Sij, which is it's a matrix made of Mandelstam invariants, although these are not immediately, these are combinations of Mandelstam invariants, because S, say, 2, 5 contains, it's the invariant that you build with all the momenta that come in between 2 and 5. So say Q3 plus Q4 plus Q5 or 2 squared. Anyhow, so you define some combination of Mandelstam invariants, and then this matrix, you add a row or a column, and it's in fact both, and those are the masses. And then the last term is just 0. Okay, so you define some matrix, and then one can show that the semantic polynomial for the generic one loop integral is really simple. And then we want to use what I wrote in the previous slide, and a simple choice is to say, okay, let's use for HI simply the numerator. But you see that here there is a sum, and so I will not use it just once, I will use it n times. So I will say, okay, I is delta, I k for some k, and so I will have exactly n equations, and there will not be sums, so this will be just one thing that I will write down, and I will take a single derivative, and I can do it n times. It's definitely a possibility, and this is what these people did way back then. And then it's the usual game. When you differentiate, you get lower powers of z. But when you differentiate the denominator, then the dimension also come into play. So in some sense, you can adjust by changing the dimension in which the integral is computed. And at this stage, is an open question whether this will converge or help. But in this case, it does. And in fact, there is a general result. Now, I don't want to sort of keep you here. I just want to give you the final result. But so it's useful to have some index notation, which I will use only here. So if you want to read your mail for a second, please go ahead. So I consider a function of n plus 1 indices, and the index set, I call it R. And in practice, for me, this is going to be the function. I'm sitting at one loop. And then I define some raising and lowering operators. I can raise by 1 or lower by 1, which means I partition the set R into 3 subsets, I, J, and K. And in the set I go down by 1 in the indices. In the set J, I stay still. And in the set K, I go up. And in this language, it is easy to, so there are identities here that are nice and actually useful. So for example, you have an identity like this. Imagine that you sum all the Fs in which you have raised one index, and you have let all the other, be there, and you haven't lowered anything, and you sum over all the indices. So this is like multiplying times Z1 plus Z2 plus Z3 plus Z4, and that is the first semantic polynomial at one loop. So this is the same thing as simply touching the n plus 1, which you have defined as the sum of all the others. So these are identities that in practice actually help, and they are easily expressed in this language. And then when you go through the mechanics, then the general equation can be expressed in terms of these raising and lowering operators with appropriate coefficients and the Mandelstam invariants, as you might expect. And then you want differential equations, you can start differentiating. And when you differentiate with respect to external parameters, you actually raise the powers, because if I differentiate with respect to S12, that will generate a Z1, Z2. So the news go up. But then you use IBPs to go down if you can, and Barucchi, Ponzano, and so this was it never had a name. We gave a name to this thing. We call it the Barucchi-Ponzano-Regge theorem. It says that you can always close the system using this technology, for the generic circumstances with any internal or external masses, everybody on shell for the external legs, you can always close the system with at most 2 to the n minus 1 differential equations. And I actually have a constructive procedure to solve the equations by series, okay? So in a moment, you might have some issues of integrability with differential systems of differential equations for Feynman integrals, but because they have an algorithm to solve it, in this case, there is no issue with integrability. They actually, in some sense, it's an existence proof by practical construction. I can't really hear the acoustics here. Yeah. So this is so for example, when I now will do a simple example, zero masses, and then now we know the answer from years of calculations, and for the massless box, the number is 3, right? But it's a box, so here the upper limit for generic numbers would be 2 to the 4, so 16 minus would be 15. So you know that any box solves a constructible system. No, that will not do absolutely anything, because if you tell me the theory, what you are really telling me is how to do Passarino-Veltman. So I have already taken the theory down to scalar integrals, and there is some loss of information there, right? If I do it this way, then I can have a general technology for scalar integrals, but then some things will be mysterious, right? Then I will use some very symmetric theory, and I will find out that there are no triangles. I reduce, and suddenly there are no triangles, and it becomes difficult to understand why. It becomes like, oh yeah, there are no triangles. That is really something that comes down in mystical ways from the symmetry that you have massacred, right? Okay, so this is one loop. And now let me make a few examples to make this concrete. This is the maps that I promised. This is called, it's the world map for fish. It is a projection that has been optimized to show that the oceans are actually a closed set. And this is the South Pole, this is the North Pole. So all I'm trying to say here is I'm proposing a different perspective on very well-known results, like the map of the world. Very good. So the massless box, here is the massless box. So R can be S over T or T over S. We chose T over S. Apologies for some inconsistency. So I'm using a notation in which the integrals, these numbers that you will see appearing, are actually nu minus 1. And this is what we did originally. And then I don't remember if it was the referee or somebody else said, look, everybody else is using nu, not nu minus 1. So in that language, this would be I 1 1 1 1. Okay, but never mind. I'm just using this convention. So you build the Cayley matrix. It's very, very simple, and then you start taking derivatives, right? You take derivatives of this one, and then you get another one. And you take derivative of that one, and you get another one, and things are going up. So you are worried that this looks like it will never close, but fortunately, you have the IBP identities, and this was actually not for the massless case, because they were very worried about infrared divergences, and not with epsilon, because they had masses everywhere, and they were regulating the ultraviolet with sphere parameters. But if you use their technology, then it suggests a basis of 4, in this case, integrals, and this is just so you start with 0, and it's easy to see that when you differentiate with respect to R, you will raise 2 of the powers of Z. Of course, this is just the simplest, and then I would have the numerator with powers of Z's, which will go up, and they will go up in pairs. So I can let 1 3 go up, or 2 4, and then I get the one with all up, and then it's not obvious that it closes, but it does close by the Barucchi-Ponzano-Regge theorem. And experts will notice that this is suboptimal. So these are 4 basis integrals, and it's overcomplete. The massless box has only 3 basis integrals, and this is potentially problematic because if you use an overcomplete basis, then you can have issues with integrability. But as I said, there is no issue, because they built an explicit solution, and in fact, we are just here following what they did, but one can do it better by choosing different HIs and just get to the basis that one wants. Yeah. Which scale numeric? So if you're imagining tensors in the numerator, I imagine that I have done a Passarino-Bergman decomposition. Yeah. Yeah, we should. I'm actually eager to understand your. Yeah. Yeah, we should. So this is really, we were at this stage, we were just doing it like the old way, if I may say, but seeing if it adapts to massless diagrams, dimensional regularization, and all the stuff that we have learned later on. Yeah. Yeah. Well. They are the box and the bubbles. Yeah. Box and the bubbles, they are the natural ones. No, these are not bubbles. These are all boxes because of this reason here. Yeah, exactly. Right, exactly. So it is not what one would normally do. It's different. Yeah. Well, what they did was observe that if you have something of this structure, then you just generate powers. So here there are some products of these, and you multiply times either Z2, Z3, or Z2, Z4, or both, and then it continue, but then you have the identity that helps to close the system. So yeah, one can do that, and if you saw the what I call sort of the master equation, you initialize it with some relatively high number value for the news, and then you take derivatives, and of course, sorry, this is really not working. Okay. So you have a potential boundary term, which could be there, and then you generate some integrals which possibly live in a different dimension, because at every stage you have to keep the homogeneity. But then you look at the boundary term, and the boundary term in this case, the integral of the boundary term vanishes, simply because this form here is 0 on all the boundaries except Z1, which is the one that falls out when you use this particular case, is h equals to 1. But when this is not 0, you have a factor of Z1 squared outside. So there is no boundary term. And then when you just do it for the 4 lines, then you get a 4 by 4. These are the 4 master integrals, the derivatives close, and you can show it. And then, of course, this is not exactly what you would like to have in modern language. It is not in canonical form. The basis is over complete, but you can still, even if you don't want to do anything smarter, you can still do it. You can bring it to a better form using Magnus exponentiation. You can bring it to a form in which you can solve it iteratively in epsilon. And when you do that, it's not difficult, then you get the answer. So that is, you can check it with Johannes's rep. Now, the next thing is the pentagon, of course. And the pentagon, there is this result by David and Zvi and Lance. I mean, of course, it was known, I guess, even at the time, that it would reduce somehow to a sum of boxes, but the specific reduction was I believe, in that paper. So, okay, to make the long story short, if I write my identity in this case, I don't need a differential equation, okay? But the definition of needing a differential equation is a bit depends on the problem, right? Because if I can come down to an integral that I know how to do, then I don't need a differential equation, right? And what happens here is that I immediately come down to a bunch of integrals that I know how to do. So I start with the news equal to 1, and this is dead, so sorry. It simply is not allowing me to project anything. Okay, first equation. I start with the news equal to 1. I write my my identity, but now the boundary term. So there are two interesting things there. The first thing is that the integral on the second on the right hand side is actually in 6 dimensions if I started in 4. And the other thing is that the boundary term in this case it actually does not vanish. So when I go to the boundary, so I drop 1 in this case because h is equal to 1, then I get an integral, and this integral does not vanish, but one recognizes it is actually a box. It would be exactly a box if there wasn't S25. It would be the massless box. But with S25, it is a box with a mass. And the mass is equal to S25. So this directly reduces, then you can build a system. The matrix of coefficients is the one that I have written there. And when you solve the system, you get exactly the BDK solution, which in particular says that when you go down to epsilon equal to 0, then you just get a sum of boxes, because this thing here, there is an epsilon in front, and this is the 6-dimensional integral, which is finite, both UV and IR, and so that's it. So we reproduce this result. And then we also, of course, the idea is to go to 2 loops. Nowadays, people will tell you, everybody can do 1 loop. And the simplest thing at 2 loops is the equal mass sunrise. The sunrise integrals, or the banana integrals, as I will say in a moment, they are very interesting. They are in principle simple because they are 2-point functions, but when you have masses, you immediately get elliptics, because if you have masses, you can cut. There is a cut with 3 massive lines. So you get very soon elliptics. In due course, you get Calabi-Yau's. There is also the original paper by Reg was considering these integrals. The first semantic polynomial is very, very simple and super and extremely symmetric, as evident it must be from the graph. So you can, if you want, define raising and lowering operators in the same way. And also here you have identities. So if I raise the particular combination of indices which builds the first semantic polynomial, this is equal to what I would get by changing the last index backwards. So these identities are useful because they reduce, or they allow you to choose some integrals that you like more. So at this stage, we just blindly play the same game. So we choose the numerator directly as our h, and we play the same game as before. And here, again, we find a non-vanishing boundary integral, but the non-vanishing, so here all boundary integrals in this banana, if you contract a propagator, then the 2 external legs go to the same point, and so they are all tadpoles. And indeed, the boundary here, you simply compute. It is this particular combination of gamma functions. And then you are down to 2 integrals. You get 2 differential equations. They are first-order differential equations. And you can combine them into a second-order differential equation by simply, this is a system of 2 first-order equations. So it naturally makes a second-order equation for the integral you want. And the equation is the original equation that was written by Remedi, possibly with Laporte. Yeah. Back in 2004, which of course in turn is a very, very interesting equation for a number of reasons. If you want to do the sunrise with 3 masses, there are some complications which we may discuss later, and I would like to close. We have also done at 2 loops. We have done the integral, this thing here, which is this is the integral, the simplest integral that was originally computed by Chetirkin and Kachov when it was a difficult integral, 40 years ago. And you can make it into a bunch of gamma functions by using IBP identities and reducing it to integrals in which you have dropped the propagator. So these would be these kind of integrals here, which are just gamma functions. So we have done that, but of course, now, this is in a paper that was published a few months ago. Now we would like to build the systematics, right? We don't want to be sitting and guessing at the best HI. So we are thinking about this, and this is all very preliminary. And on the other hand, as I said before, there are algorithms which are up and running that use Feynman parameter techniques, and so, who knows, maybe we will simply find that what they did is already optimal and there is nothing to do, so we'll see. Okay, so just to give you the gist of what we think we can do, it's the following. So I write my equation and I just flip it. I bring the stuff I want to compute on the left-hand side, and this is the complicated, and this is the difficult thing. And it is now equal to two things that are simpler for two different reasons. One is because P is lower, and one is because it's a boundary term. And so the idea is I have some integral, and I want to decompose it. And so the Q of that integral, I want to write it as this, right? And what I have done before is just guess some useful HI. Now, what you can do more generally, what you can do automatically is you say, okay, I can compute these derivatives, and then I can assume that there is a polynomial ring which is generated by these n polynomials. These are n polynomials. Now, technically, one has to be a bit careful. There will be a piece which will be to the power epsilon. And we have found that you could go ahead and keep it, but it's better to just look at the coefficient of that and put back the piece to the 1 plus epsilon or whatever it is at the end. And then once I tell you that I have a polynomial ring, there are tools to decompose. So I have some polynomial here or some monomial, and I want to decompose it in a ring. And I use, for example, we have been using singular. So I find the HIs. They are typically not super simple, but it's, of course, we have only done very simple cases, but sort of this would be the general logic, and one has to be a little bit attentive. We leave out epsilon-dependent powers, and then step by step, one must impose the symmetries. So, for example, if I have the sunrise with equal masses, it has a symmetry in the exchange of the three Feynman parameters, and that's why I compute an integral, and then I know also all the others. So this is fairly trivial. And this is an example of the identity that I was mentioning. So if you raise indices in the combination that corresponds to the first polynomial, then this is the same thing as raising the other one. So this can help. So at every step, in the cases that we have looked at, we have only at most 2 steps, but you try to use this to see if it helps, and then eventually, if you need, you iterate. And we have been, for the moment, looking just at bananas, which are sort of a natural playground because they have only a single external parameters, so you don't get very large system. But ultimately, of course, the logic would stand. So roughly speaking, I could say somebody whispers in our ear that these are 2 of the basis integrals. If nobody whispers, you can still figure it out, right? Actually, it's a sort of trivial one when you use this approach. Then you have your basis polynomials have a certain degree, say 2 or 3, and so anything which is of lower degree is not decomposable, and so you say, okay, I'll put that in the basis. And then when you get to higher and higher degrees monomials, then they become all of them, they will be decomposable. So there is a bracket in which you have some choice, but when you go too high, everything is doable. And when you go low, that's where your basis integrals are likely to be. So if we have those, then you differentiate, and then there is one integral which is not, is new. You use identities and symmetries, and then when you have isolated the single integral you want to compute, you use the procedure that I described in the previous page. You have a sum of terms which are derivatives of this h, and when you put them, they look complicated, you put them all back together, and they become super simple. The boundary term does not vanish, but it's a tadpole, and so you get the solution for the sunrise. And actually, what we have used is 3 equations, okay? The master equation we have used once for a single integral, and we use 2 constraint equations, so total of 3. If you take that integral and you dump it into Kira, for example, and you don't try to be too smart, just see what happens, Kira will typically generate about 50 equations. And then if you look with a flashlight, then you realize that maybe it uses only 7 or 8 or 9, depending on exactly what you have done. And this is now 3 equations. And if you go to the 3 banana, so the 3 loop graph, then again, we assume for the moment that there are a bunch of integrals that are the beginning of our basis. Use identities and symmetries, and you find that there is only one that you need to look at, but here it's already more delicate because you have a menu of choices for the last integral, and some choices don't work well because you get negative exponents when you differentiate, so you have to be a bit smart, which is what we don't want, right? An algorithm, you don't want to have to be smart. You want to push return and get an answer. But here in various places, we still have to be smart. So when you take derivatives, you generate a new integral, and in this case, you have to iterate. So you have to do it again. Again, you have to put your hands in it. It's not fully automatic. The boundary terms are tadpoles. That will always be true for multi-bananas, or in some cases, they vanish. At the end of the day, we get the result, which means getting the result here means having a closed system of differential equations. We're not solving the equations, right? So we get the result, we're using the master equation twice and using the constraints a total of 5 times. So that's 7 equations that we are using. Again, if you dump it into Kira, Kira will generate about 900 equations, out of which then you look with a flashlight and a few tens of equations are actually used. So it's fun. I mean, we are optimistic, and we are also trying to understand, what an IBP is doing. I know that some of the technology is different. They're using syzygies, and which we totally we don't know, therefore don't use. Okay, so the beautiful outlook of Florence. Digging back into ancient history, you may find treasures. And what it says in the second line is wrong. What this old language is being translated. Feynman parameters really seems to be, I believe, the best way for a number of reasons. So first of all, there are no redundancies. The symmetries of the graph and the general graphical properties are openly encoded in the Feynman parameter integral. There is beautiful mathematics. It's the mathematics of projective space. The differential equations that you get are related to monodromies. And monodromies means solution, monodromies around what? Around the solutions of the Landau singularities, which means that this is related to unitarity and to a lot of activity which is currently being done in this field. And if you look at the master equation that you generate and that I wrote down, it goes downhill. So it is oriented, okay? And if you use Laporta puts some random seed, and then in this lattice of integrals, you go up and down, and you dig and search, and then at some point you hope it will close, and ultimately there is a theorem, it will always close. But in complicated cases, you generate millions, of equations, tens of millions of equations, right? So the idea of having something that goes downhill, so that I give you something complicated and you only get something simpler, is potentially very powerful, and it does seem to help in the simple cases that we have looked at so far. It's recursive, but it goes always in the same direction, and we are trying to go forward, obviously. And thank you.
Sorry, hi. Sorry, just so are the monetary, how easy are the monodromies to compute? I mean, there's this famous Riemann-Hilbert problem that reconstructs the differential equation from its monodromies. So is there a route there that's been explored for our Riemann-Hilbert problem?
I don't know enough mathematics to answer that properly. My impression is they are very complicated.
Sorry, so the
monodromies are complicated. So in these old Reggio papers, that's what they do, right? They construct a matrix representation of the monodromies for these classes of integrals, and these are very, very hard papers, both. And I cannot claim I understand it. So the monodromies are hard, but we don't need the actual monodromies, right? We need dimensions, and we just sort of looking at monodromies would give you a slightly different kind of information, right? Which is very interesting, but not we are not using it.
Can I make a comment regarding the monodromies, since this was raised? So at least for one loop integrals, there is a complete understanding through the grammatic coaction. And there, I mean, it's possible to see that's more general than one loop, but one loop, it's very explicit that the coefficients of the differential equations are obtained from cuts. They're basically limits of cuts and then limits of cuts.
Right.
So there is a very explicit construction of what would be the coefficients in terms of cuts.
Right.
Of the same integral.
Right. So this is, I think that what, but
there's a very explicit result.
Yeah. I am slightly worried in terms of, if you look at the grammatical action, about multidimensional singularity. So when you're going around not a cut, but a two-dimensional surface of singularities. But I have very little understanding of them. I don't know. Yeah, you know what to do. That's the. Yeah. Yeah. Okay. 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 Very good. Thanks.
Can you go back to the transparency with the rearranged master equation? So, yeah, I think this one. So at one loop, I think it's plausible, it's not obvious to me in this language, that Q in fact always decomposes over the derivatives of D.
Yeah.
And it's undoubtedly true in some examples at higher loops like the bananas, but in general, it's not going to be true.
Yeah.
So there's going to be a remainder term left over.
Very good, thank you. So a typical problem that you run into is that you go down and you find something that does not decompose, that it has a remainder. So in the cases that we have looked at, it is all what we have done is looking at linear. First of all, you use your constraint mapping integrals around, and then you pick a linear combination, and we have always found a linear combination of available integrals that is reducible. In the general case, it is possible that you will hit something that is not reducible, and then you would have to go deeper and make an actual Gröbner basis, or you can deal with the remainder, right? So of course, this will just for me, there will be a remainder in the polynomial division, and I will have to treat that as a new integral and see how bad that is. But if you want the really short answer is I don't know. I know it is a problem. It is a problem that we have seen, especially in the three-loop banana. It happens, and we found a solution easily. And but we don't know in general. It's a problem. Yeah.
You never get differential equations in epsilon.
I never get.
You never get differential equations in epsilon.
No, I will never. I'm only differentiating with respect to external parameters.
Yeah,
would be fun. I never thought of it.
That's a mad question. Okay.
Yeah. No, you see, I'm tying together integrals, and then the idea of making differential equation comes from outside, right? So somebody at some point said, "Hey, you can take derivatives," and then the nice thing is that the derivatives map back into the same set, and then. But it's always derivative either with respect to Mandelstams or principal masses.
I just want to ask, in DimReg, we have one regulator. In the spear thing, how many regulators do we have? How many lambdas do you have?
One per propagator.
Isn't that just overly complicated?
You know,
or do you use
people started back then with the most general idea, and then what you would do is just, you know, call them off. Presumably call them all lambda. I don't exactly know what they did.
But is that useful for something? The spear one?
I don't know what do people do nowadays with analytic regulators. I think people shift the power, all the powers of the propagators by the same amount. That is typically sufficient. But it's not necessary. I mean, I can imagine some cases in which the trouble comes from a subdiagram, and then maybe you only want to regulate that, and so you let the lambdas, the spear parameters be 0 somewhere, and you just fix the ones you need to fix. So there is a freedom there.
Okay, not, let's thank Lorenzo again.